ഞാനേ എനിക്ക് പിന്നെ ചുമ്മാ ക്ലിയർ വന്ന
Good morning to all. In previous class, we are discussing about the heterocyclic compounds. In these heterocyclic compounds, what is the classification and the nomenclature of heterocyclic compounds? Then, in this topic, we are discussing about the 5-membered heterocyclic compounds as well as 6-membered heterocyclic compounds. So these are the 5-membered heterocyclic compounds. Those are furan, thiophene, pyrrole. Then, so here, these in 5-member ring system, 5-membered heterocyclic compounds, the totally 6 pi-bonded electrons are present, and those are involved in the resonance. That's why it is having aromatic nature. This is about the aromaticity of 5-membered or 6-membered heterocyclic compounds. The next, we are discussing about the resonance structures of 5-membered heterocyclic compounds. So in these 5-membered heterocyclic compounds, the heteroatom is having the lone pair of electrons as well as 2 pi bonds are present. So totally these 6 pi bonded electrons are involved in the resonance. So that's why it is having the aromatic character. Look at this. In this picture, this halogen atom is having the lone pair of electrons. Those electrons are donated in between the halogen and the carbon. Double bond is takes place. Automatically, the pi bonded electrons are shifted to the next carbon that get the negative charge. It is shown in figure 2. Then in the next step, these negative charged electrons are polarized in between the second and third carbon. Double bond is takes place. Automatically, the pi bonded electrons are shifted toward the fourth carbon. Then this type of structure is produced. In this negative charged carbon ion donate the electrons in between the carbon and halogen. Double bond is takes place. Automatically, the halogen carbon containing the pi bonded electrons are polarized toward the carbon. Then that carbon get the negative charge. This is the complex. Then in this, the negative charged electrons are shifted in between the 2 carbon atom, that is first carbon and second carbon. Automatically, the pi bonded electrons are shifted toward the third carbon. Third carbon carries the negative charge like this. Okay. In this next, these negative charged electrons are shifted in between the third and fourth carbons. Automatically, the fourth carbon and halogen is having the double bond. Those electrons are shifted toward the halogen. Then halogen is having the pair of electrons. How we can explain this 5-member ring is aromatic compounds. Look at this. In this, the 2 pi bonds are present. 1 pi bond requires 2 electrons. So that's why 2 into 2 pi electron, that is equals 4 pi electron. And the heteroatom is having lone pair of electrons, that is 2 electrons are present. So that's why 4 plus 2 is equal 6. So 6 pi bonded electrons are involved in the resonance. So that's why we explain that. So this 5-member ring is having the aromatic character. The next we are taking about the pyridine. In this pyridine, totally 3 pi bonds are there. 3 pi bonds is nothing but 6 pi bonded electrons. As well as nitrogen atom is having the pair of electrons. But the nitrogen atoms, pi bonded electrons are not involved in the resonance. Only the carbon, the in 6 member, this pyridine, the only pi bonded electrons are involved in the resonance. And this structure also obey the Huckel's rule. That is called the 4n plus 2 pi electron system. So that's why it is also the best example for aromaticity. And in this class, we are discussing about the preparation of heterocyclic compounds. The first preparation method is polymer synthesis. So what is polymer synthesis? 1,4-dicarboxylic compound. It is also called as succinic dialdehyde. It is reacted with phosphorus pentoxide and it is converted to furon. Then let us see what is the mechanism is involved. Look at this. In this structure, the carbon atoms, that means the C double bond O attached carbon, 2 carbons are having the 2 hydrogen atoms. So one of the hydrogen donate the electrons in between the carbons and it is eliminated as proton. That proton is attracted by the C double bond O carbon, because when the electrons are polarized, this hydrogen donate the electrons in between the carbon, automatically the valency of the carbon is increases. Then oxygen carbon pi bonded electrons are shifted toward the oxygen atom. Oxygen get the negative charge. Then the eliminated proton is added to O minus. Then this type of structure is produced. In this structure, the 2 OH groups are present. One hydroxyl group is eliminated as OH minus. Then carbon get the positive charge. And another OH group, this hydrogen is eliminated as proton. Then oxygen get the negative charge. So the negative charged oxygen donate the electrons to positive charged carbocation. Then it is converted to this type of structure. It is called as furon. Then next take another one, that is preparation of pyrrole by the polymer synthesis only. In this reaction also we can take the 1,4-dicarboxylic compound. It is reacted with ammonia. Under heating, it is converted to pyrrole. Let us take the mechanism. So in this also the above phenomena takes place, just like the carbon, the C double bond O attached carbon, the 2 CH2 carbons are there. Those 2 CH2 carbons, one of the hydrogen donate the electrons in between the 2 carbon atoms, that is one carbon and another one is aldehyde containing carbon. Okay, then that hydrogen is eliminated as proton, as well as the carbon-carbon valencies increases. At that moment, the carbon-oxygen pi bonded electrons are polarized toward the oxygen atom. Then oxygen get the negative charge. That negative charged oxygen atom attracted by the proton, the H plus ion is attracted by the nucleophile. So that's why OH group is produced like this. So this OH group, the 2 carbon atoms are having the 2 hydroxyl group, that is reacted with NH3. In NH3, the nitrogen atom is having the 3 hydrogens. Okay. In these 3 hydrogen, one hydrogen is reacted with OH, then it is eliminated as water. Another hydrogen also reacted with OH, that is also eliminated as water. So that's why in this reaction, 2 moles of water is eliminated. Then it is converted to pyrrole. Then the third component is thiophene. How we can prepare thiophene by the polymer synthesis. In this also, we can take 1,4-dicarboxylic acid, dicarbonyl compound. So this 1,4-dicarbonyl compound, it is reacted by loss of water. Look at this once I repeat it. 1,4-dicarbonyl compound is reacted with the hydrogen sulfide or P2S3. Under heating, it is converted to thiophene. So in this reaction also, the above phenomena takes place. So here, the carbon is having the two hydrogens. Okay, C double bond OH containing carbons are having the two hydrogens. So in these two hydrogen, one of the hydrogen donate the electrons in between the two carbons, and that is eliminated as proton. Automatically, the valency of the C double bond O carbon is increases. Then carbon oxygen negative charged electrons are shifted toward the oxygen atom. Then both the oxygens are having same phenomena, and oxygens get the negative charge. And this negative charge O minus, it is attracted by the proton. Then it is converted to 2OH groups. 2O minus is converted to 2OH. Then it is reacted with hydrogen sulfide. The 2 moles of hydrogen is sulfur group is added to the 5-member ring. So this is the preparation method of thiophene. So these are the another preparation method of furan. So in this reaction, we can take the furan to aldehyde. It is called as perfuraldehyde. This perfuraldehyde under oxidation in the presence of potassium dichromate, it is converted to furoic acid. Under heating, this furoic acid lose the carbon dioxide and it is converted to furan. So this is the another preparation method of furan. Then next take the another preparation of the remaining compounds also. In this process, we can take the 2 moles of acetylene. It is reacted with the hydrogen sulfide in the presence of the red hot copper tube, that is converted to thiophene. Then the next method is preparation of pyrolysis. In this also we can take 2 moles of acetylene, that is reacted with the ammonia under heating in the presence of red hot copper tube. It is converted to pyrrole. The next is about electrophilic substitution reactions of heterocyclic compounds. Look at this resonating structures. In these resonating structures, this the group, that means the heteroatom, that is hex. Hex attached in same positions are toward the left side and toward the right side of the heteroatom. So that's why two alpha positions as well as two beta positions are present. So here in this, the alpha and beta carbon, it is having the pair of electron, it is having the pi bond. So these pi bonded electrons are shifted toward the alpha carbon. Then alpha carbon get the negative charge. So this negative charged carbon ion, it is reacted with electrophile. Then, so this type of structure is produced. So attached carbon is called as beta. Beta carbon is having the positive charge. Then the toward the left side position of the heteroatom, alpha and beta carbons are having the pi bond. So these pi bonded electrons are shifted in between the two beta carbons. Then the alpha carbon get the positive charge. Okay. Then this heteroatom pair of electrons also involved in the resonating structure. So due to that reason, this heteroatom containing pair of resonated in between the alpha carbon and beta. Okay, the resonating structures are takes place vice versa, and electrophilic substitution is takes place. So this is regarding for the electrophilic substitution reaction. Why the electrophile is substituted at the alpha position? Because the electrophile is substituted at the alpha position due to the this alpha position carries the electron. The alpha carbon is acting as the electron rich center. So that's why it is reacted with the electrophile and it is involved in the electrophilic substitution reactions. Okay, beta position also negative charges takes place and electrophile is attacked at the beta position and it produces a less amount of resonance structures. So that's why alpha position can give the more resonating structure. So that's why when comparing with the beta substitution, alpha substitution is more stable. The next one is electrophilic substitutions of furan. Okay, we can take the furan. Furan is a colorless liquid. It is ionizable in water but soluble in the nonpolar solvents that are the benzene or chloroform, whatever the solvents. In this also, electrophilic substitution reactions process in mild condition only. In strong acidic medium, heterocyclic compounds may polymerized or ring cleavages take place. Once I repeat, in furan, also it is also involved in the electrophilic substitution reaction. So the electrophilic substitution reactions are takes place in mild condition only. But in the presence of the acidic medium, polymerization is takes place or ring cleavage should be takes place. Let us take nitration reaction. Furan is reacted with the nitric acid in the presence of electrophile, that is the NO2 minus. So in nitration reaction, NO2 minus, it is called as electrophile. And the electrophile is attacked at the alpha position rather than the beta position, because when the electrophile is attacked at the alpha position, it produces the most stable product due to the resonance structure. Okay. Then it is involved in the sulfonation also. In this sulfonation, the sulfonic acid group is attacked in the presence of the pyridine and produce the furan 2-sulfonic acid. As well as this furan involved in the halogenation reaction. But the furan directly, it is not involved in the halogenation. In this process, we can take the furoic acid. So this furoic acid, it in the presence of heating is converted to furan. Then only it is, once I repeat again, furoic acid in the presence of the chlorine and AlCl3 Lewis acid, it is converted to alpha chlorofuroic acid. So this alpha chlorofuroic acid under heating, this carboxylic acid C double bond OH, it loses the carbon dioxide gas and converted to chlorofuron. Then next is, so this furan, it is also involved in the Diels-Alder reaction because furan, it is having the 2 double bonds. So that's why it is acting as the diene. And it is reacted with a dienophile, that is ethylene, and it converted to a adduct. So adduct is nothing but product. Let us take this reaction. So here in this mechanism, this ethylene, see double bond is there. So double bonded, the 2 carbon atoms are having a double bond. So that double bonded electrons are shifted towards the furan alpha carbon. Then that alpha carbon and this dienophile, it is having a sigma bond. Automatically, the pi bonded electrons are polarized in between the 2 carbon atoms. Double bond is takes place. Okay. The next, this alpha beta positions also having the double bond. So these double bonded electrons are shifted toward the carbon. Then this carbon having the negative charge. So these negative electrons are donated toward the dienophile because the dienophile one carbon is having the positive charge. Then these negative charged electrons are donated toward the positive charged carbocation. So this type of adduct is produced. Then the next reaction is furan is reacted with acrylaldehyde and it produces this type of adduct compound, as well as furan is reacted with malic anhydride. It is also produce a adduct product. The next is reduction reaction. What is a reduction reaction? This furan is involved in the reduction in the presence of the nickel at 125 degrees centigrade. The unsaturated compound is converted to saturated compounds. Instead of the 2 double bonds, the 4 hydrogen atoms are added to the ring and it is converted to tetrahydrofuran. Okay. Then the next one is, what are the chemical reactions, okay, of thiophene? So in the previous we are discussing about the furan. Next compound is thiophene. Thiophene chemical reaction. So it is also more aromatic than the furan. It is also a colorless liquid and insoluble in water. Thiophene undergoes electrophilic substitution reaction at alpha position due to the more stability of carbonium ion. Already I told in for the furan also. In all the 5 member rings, the alpha position give the more stable product when comparing with the beta due to the resonating structures. Let us take this thiophene. It is involved in the nitrate added at the alpha position, and it is called as 2-nitrothiophene. Then the next one is this thiophene. In the presence of the cold sulfuric acid, it releases the sulfonic acid, and that sulfonic acid group is attacked at the alpha position. Then it is called as thiophene 2-sulfonic acid. Then the next reaction is, in the previous class, the furan is not directly reacted with the chlorine, but here the thiophene, it is directly reacted with the chlorine at minus 30 degrees centigrade. It produces two types of product, that is 2-chlorothiophene as well as 2,5-dichlorothiophene. So these are the chemical reactions or electrophilic substitution reactions of thiophene. Then this thiophene also involved in the reduction in the presence of the palladium as well as the nickel. So in the presence of the palladium, it only the double bond is involved in the only the double bond is involved in the saturation, and it is converted to tetrahydrothiophene. Then the next one is, in this also the thiophene, it is involved in the reduction in the presence of hydrogen nickel. In the presence of the Raney nickel, it is converted to N-butane. Then the next chemical properties of pyrrole, it is also called as pyrrole. The pyrrole also involved in the electrophilic substitution reactions at alpha positions. Let us take, this is pyrrole. This pyrrole, it is involved in the nitration in the presence of the nitric acid and acetic anhydride. The nitronium ion NO2 plus group is attacked at the second position or alpha position. Then it is converted to 2-nitropyrrole, or it is called as 2-nitropyrrole. And this pyrrole, it is involved in the sulfonation also. The sulfonation reaction, it is takes place in the presence of SO3 and pyridine. The sulfonic acid group is substituted at alpha position. Then it is converted to pyrrole 2-sulfonic acid. And this pyrrole, it is reacted with thionyl chloride under heating. The four chloro groups are substituted at the alpha and beta positions. Then it is converted to tetrachloropyrrole. The next is about the reduction reaction. This pyrrole, in the presence of the hydrogen palladium, it is involved in the reduction and it is converted to tetrahydropyrrole. Okay. Then next is about, it is involved in the Riemann-Tiemann reaction. So this pyrrole, in the presence of the chloroform and potassium hydroxide, it is converted to pyrrole 2-aldehyde, as well as it is converted to 3-chloropyridine. So the various, the different types of products are produced in the Riemann-Tiemann reaction. So this is the mechanism. of Rimmer-Timmer reaction. So in the Rimmer-Timmer reaction, the chloroform CHCl3, it is converted to dichlorocarbene. So here the carbon is having the pair of electrons and empty orbital, and two chloro groups, it is called as dichlorocarbene. So this dichlorocarbene, the carbon atom is having the pair of electron. So those electrons are donated toward the beta carbon. Automatically the alpha beta containing pi bonded electrons are shifted toward the electron deficient center of the carbene. Then this cyclic structure is produced. Then next it is converted to this type of product.